Okay, all hello. Thanks for having me this afternoon. It's exciting to be here. As Mark mentioned this morning, this is probably going to be my last affiliates forum unless I am invited back by some special request to talk about the research that I'm doing down at UC Berkeley for my PhD dissertation. Over the last couple years, I've been spending part of my time here at the Cooling Efficiency Center and working on the project that I'm going to share with you today, focused on developing what I would consider, and will be happy to argue with about, a universal model for hybrid air conditioning systems for use in Energy Plus building energy simulations. I've been working on this project for a couple years, as I mentioned, had a lot of help at the beginning from Nelson Dichter. Been collaborating with Lawrence Berkeley National Labs and with NREL, Spencer Dutton and Daniel Studer over the last couple years to bring this project together. And then also a whole slew of undergraduate students who have been working with me over the past couple years through a project funded by the Department of Energy that focused on kind of extending our integration to undergraduates, training them in building energy simulations, getting them involved with and participating with our industry partners, and learning about energy efficiency in buildings. So I want to give very quickly an overview of what we're talking about when I say hybrid HVAC systems. Of course, a lot of our work here has been focused on different types of evaporative cooling technologies, especially pre-coolers for condensers. But I think of hybrid systems as a much more general category of equipment that includes many different types of cooling, ventilation, or heating components that are integrated together into climate-appropriate ways that operate in multiple modes of operation to provide heating, cooling, dehumidification, and ventilation as needed with the highest efficiency possible by coordinating all of those modes of operation throughout time. A lot of hybrid air conditioning systems also have a great advantage because they integrate component operations in very mutualistic ways. So I've given an example here on the slide of the Munters EPX 5000, which uses indirect evaporative cooling together with vapor compression. The indirect evaporative cooling component is the block shown in blue in the middle, and the vapor compression system is the loop shown in orange surrounding the indirect evaporative cooling component. So this is a dedicated outside air system, brings in 100% ventilation air over on number 1, runs it through an indirect evaporative cooler. For many periods in time, the air cooled by indirect evap is enough to carry the loads in the building. When it's not, it can cycle on to provide vapor compression cooling as well. And one of the interesting aspects about the way they've designed the system is that the condenser for the vapor compression system is sitting in the exhaust stream from the indirect evaporative cooler, and therefore gains some of this, I'd call, mutual benefit of integrating the two different systems together as a hybrid. Of course, there are many different types and architectures for hybrid systems. Just some of the advanced technologies that they might include would be variable speed fans and compressors, ventilation heat recovery, desiccant dehumidification, indirect evaporative cooling, and, as I mentioned, condenser pre-cooling. Really, the best strategies differ by climate, and I know that it's always frustrating in our reports to read, well, the answer about how much energy it saves is, it depends. But it really does. And through the work that we're doing here, I hope that we're going to be developing a tool that will help practitioners to understand what are the most appropriate hybrid solutions in particular buildings and particular climates. Some of our studies have shown, however, that hybrid air conditioning systems, in this case the dual evaporative pre-cooling, can reduce peak demand by 40% or more. And some of our preliminary estimations show that other hybrid systems can reduce annual cooling energy by 65% or more. But why do we need a standard model for hybrid unitary HVAC equipment? Well, in particular, there are many unique hybrid system strategies. For a paper that we're writing about this subject, I've recently been surveying lots of academic literature and trying to tally up all the different ways that smart people have come up with innovative strategies to integrate hybrid systems. There's easily more than 50 different architectures, and every building is going to need a slightly different strategy, even if there are generally standardized approaches. So current building energy simulation tools aren't capable of modeling these hybrid systems. Perhaps some of them to a limited degree, but there's no tool out there right now that can be utilized to compare every different hybrid system strategy. It's also really infeasible, I'd say, to expect practitioners in the field, our engineers that are designing our buildings and trying to run parametric analyses to make a choice about different equipment design strategies, to build up models of hybrid systems from first principles. I've really only seen a couple examples of engineers doing that, and when they do for a project, they basically only manage to model one alternative in a reasonable amount of detail. And I'd say that it's a big problem that all manufacturers building hybrid systems are running against. Engineers can't consider your equipment for installation in the building, so therefore they're not going to consider them. There have been a fair number of previous simulations, especially by academics who come up with some type of unique hybrid system architecture. But in all of the reading that I've done on this, it's almost impossible to compare one author to the next and one study to another, because, as I mentioned, every application is unique, every building is unique, every model is unique. So you see all kinds of savings that all kinds of claims that a particular hybrid system might reduce energy use by 50% or 65 or 70 or 90%, but everyone's running on a different baseline, and there's really no study that coordinates all of them in a singular way. The panel this morning was really great in discussing the needs for utilities and third-party program managers in having reliable models that can generate trusted numbers about the energy savings from these equipment. So our approach, as I mentioned, was to develop a technical model, but it's important to me that we not just develop a model that can run in a simulation program, but also the entire ecosystem that's going to support bringing the data from people who know how a system will perform to the people who need to model it for their building at the end of the day. So this is the strategy that we've come up with. We've coordinated a lot with NREL to utilize some of their existing web-based infrastructure for cataloging and databasing performance information for different types of energy end-use equipment and buildings. The strategy starts with and really relies on manufacturers publishing data into this ecosystem so that it can ultimately be used. And I'd say that the manufacturers that publish data will benefit from these public modeling capabilities. We've gone to great lengths to make the submission of information pretty straightforward through Excel and through this web-based program, which I'll talk about a little bit more about. We're asking manufacturers to upload performance data to this service called the Technology Performance Exchange, which automatically populates a database for end users hosted by National Renewable Energy Lab called the Building Component Library. And then ultimately, end users would utilize our building model called the Hybrid Unitary HVAC system for Energy Plus. I want to talk a little bit about those pieces in the ecosystem. NREL's Technology Performance Exchange, first of all, is I'd say a pretty large clearinghouse for manufacturers and third-party test centers to upload performance information for very particular products. I've zoomed in here just to show you that there are already about 2,600 HVAC products that are available through the Technology Performance Exchange. We're building out a category here for hybrid air conditioners. All of the data that goes through the Technology Performance Exchange automatically gets uploaded to this service called the Building Component Library, where a modeler can go and download a snippet of an input definition file for Energy Plus and integrate it directly into whatever custom building model they desire. So the basic formulation of our model is, importantly, an empirical black box. We've designed the structure of all the inputs and outputs to that black box in a way that I think should be able to generally accommodate almost any unitary HVAC system. That means we could use it to model even current advanced refrigerant-only HVAC systems in addition to these hybrid air conditioners. All it requires is that it fit the format where the machine has return air, outdoor air, and supply air streams. We have the model set up in a way that it can accommodate the consumption of electricity, water, and up to 2 other fuels. So that could be chilled water from a central plant or perhaps natural gas. Most importantly, this model doesn't require the end users to know anything, really, about how the system performs internally. And it structures all of this in a way that allows the hybrid systems to have multiple operating modes. So I want to discuss quickly why we chose to develop a black box model instead of what I'd call a subcomponent-based modeling approach. You can see a comparison in general of these 2 different strategies on the right-hand side of the slide. As I mentioned before, it's really that it's infeasible for every practitioner to develop a component-by-component model, especially if they're trying to develop that model from first principles. One strategy could be to, let's say, come up with standards for how to represent the performance of every possible subcomponent that might exist in HVAC systems, and then have a standard way of integrating all of the inputs and outputs from those subcomponents into a building energy simulation model like Energy Plus. That's technically reasonable, and it provides a lot of flexibility for the end user, but it relies on every end user to basically invent and create the coordination of all of those subcomponents. And I'd say that it overlooks the fact that there's a lot of creativity, detail, and innovation that manufacturers are providing by coming up with real strategic products. And it's not so necessary to rely on the end user to do that. I think it's also less reliable to expect every end user to develop appropriate hybrid systems in this component-by-component approach in a reliable way that's consistent enough for standards and representation for utility models. The black box model that the black box model approach that we've developed, I think it's important to note, would have every single product with its own empirical data set. So the interface through the technology performance exchange we've developed in a way that's really clear and straightforward. It starts with a web-based form where a manufacturer would provide lots of general meta information about the product. So if it has some sort of certification, if it has a particular model number and model name, all of that information goes in here. If it has general rated performance characteristics, that gets put into this form. And then we've developed a very clear Excel template for manufacturers to provide the explicit performance data for every single mode of operation across all of the different independent variables that could be necessary or could impact performance of the machine. Doing that, it's very important to think about all of the different discrete modes of operation that a hybrid system might operate in, and this is really where that empirical structure begins. I think of a mode of operation as a distinct combination of different system subcomponents, and I think the important distinction to make here is that a lot of folks, when thinking about controlling a system, think of modes like occupied or unoccupied or ventilation or economizer mode. All of these are kind of, I'd say, intentions of what the machine is trying to provide for the building at a particular point in time. But this model really thinks of the different modes of operation as different constructs of combinations that the machine can actually operate in. So from that perspective, something like ventilation to provide indoor air quality turns out to be exactly the same as an economizer mode. So in all of the pilot data tables that we've developed, for that situation, you'd have one mode of operation that spans a wide range of outside air fraction and perhaps a wide range of supply air flow rates. And then going deeper into that performance map template, this Excel spreadsheet, there's some more meta information about each mode of operation, and then kind of a step-by-step process to answer a bunch of questions that describe what independent variables impact the performance for the mode. So we ask questions like, does performance in this mode depend on the humidity of the return air? And does the equipment consume water in this mode? By answering all of those questions, as we've done here for the Munters humidity control unit, we will automatically populate the independent variables in a data table to provide performance information for. The other piece in this performance data template is it's important to define the range of operation for each mode. First of all, we ask for the range that the manufacturer has data available for, but then also in step 4 here, we ask for a definition of the limits for which a model is allowed to extrapolate from those data sets in order to make projections of how that same mode of operation might run somewhere beyond the data that's available. From all of that information, we populate in these orange cells all of the different independent variables that we'd like performance information for, and we ask the manufacturer or third-party data provider to populate everything in the green cells. With this, we're able to run our model. It turns out there's quite a lot of information that's required in this kind of empirical construction, but for a simple DX rooftop packaged air conditioner, it's really not beyond the type of data that manufacturers are already providing manually at this point in time in engineering reference manuals. We've also been collaborating with the 3 manufacturers listed here to pilot test the model. They've been working together with our undergraduate students to populate some preliminary performance tables for their hybrid equipment for integration through our model. The manufacturer partners have been submitting these initial performance maps, at least to us right now. As soon as our new module in the Technology Performance Exchange is live, we'll be submitting them there. The 3 pieces of equipment that we've been modeling are Integrated Comfort's dual evaporative pre-cooling, Sealy's Climate Wizard, and Munters humidity control unit. Going too far there, sorry. Okay, great. So, as I mentioned, we're integrating this model into Energy Plus, and we're at a point now in the development that we have a complete input structure available in what right now is just a development version of the model, but we are expecting that we will reach the public release of Energy Plus this fall. I think that would be September or October. In the meantime, if anybody is interested in working with us to kind of pilot test that model, we'll be happy to share with you the development version. We have a few of our undergraduate students that are going to be working with manufacturers this summer. Thanks everyone here who's volunteered for that, to be pilot testing this model with the equipment that we described there. I'll give you, as quickly as I can, an explanation of how this model is working internally. On the left-hand side, we've diagrammed here all of the inputs that come from an Energy Plus building model to our model of the hybrid air conditioner in each time step. So the building energy simulation has information about all of the environmental states. So that's the outside air condition, the return air condition in each time step. It also has knowledge of the requested thermodynamic outputs from the system. In each time step, the building energy simulation knows what the set point is and how much cooling is needed in order to reach that set point. So it passes on information like, I need so many watts of cooling over the next time step in order to reach the condition I desire. The simulation also may have constraints on what supply air temperature and supply air humidity the hybrid system needs to deliver back to the simulation program. So at the very top here, I've shown what would be the empirical configuration, all of the information that was submitted through those Excel spreadsheets and translated over into a format that Energy Plus can read. That really dictates all of the choices that the hybrid system could operate in each time step. And the function of our model is ultimately to look at all of the requested thermodynamic inputs and constraints from the simulation program, look at all of the possibilities, and choose the optimal settings for operation in each time step in order to meet those constraints. After doing so, we report back to the energy simulation program the amount of sensible cooling, the amount of latent cooling, the supply air temperature, energy use, water consumption, fuel consumption, and some other meta-level information. So working with our students, we've been developing a few different baseline models with our manufacturer partners to pilot test this module. We've developed a retail building shown here, a different retail building that also accounts for transfer air between zones, and an industrial warehouse building in which we're going to apply indirect evaporative cooling. All of that work is going to continue through the summer, and by the end of September we should have both a publicly released model and a whole bunch of pilot tests to demonstrate the performance of the model. I think I'll stop there. We have listed here some of our model validation, at least in a preliminary form, and our next steps, but I'm happy to take any questions. Mo. We would be looking through all of the performance data that manufacturers supply. The data that we're expecting manufacturers to provide would span across the entire range of environmental conditions in which they would expect that machine to be able to operate.
There is any point data, will it be predicting based on this data, or everything has to be in the
Clearly, you wouldn't be able to provide every possible combination of every single point, because it would be an infinite amount of information. So what we have constructed is a data table that spans a reasonable range in each of the independent variables, and within the data that manufacturers provide, we interpolate. That would be a different approach. I'd describe that sort of as a component by component based modeling approach. And as I mentioned, certainly that would work. I'd say that there's a limitation in that because right now we might have a good understanding of the physics for a DX system, and we could populate some of those kind of metrics by which we could prescribe a somewhat theory-based model about a DX system, or for an evaporative system we could use effectiveness to project how an evaporative system would work. But there's lots of other components out there, and there may be more components coming around the corner which we don't know the physics for exactly. So in order to have a structure that can adapt to every different manufacturer's needs, we've chosen to go more an empirical route. I wonder if Mark was about to ask the same question, actually. Mo's asking about how the control strategy for a hybrid system may or may not be different than the way that we're making our decisions. You can think of our control strategy implemented through simulation as choosing the optimal in each time step. We look through all of the possibilities of all modes that could run at any point in time, and we choose the setting that will satisfy all of the requirements and constraint from the energy simulation program with the least amount of resource consumption. That may not map exactly against what manufacturer's control strategy would really be. I'm sure it doesn't. But it does escape from the need for now every energy modeler and practitioner in the field needing to define a detailed control sequence. However, at the same time, we're structuring this modeling program in a way that if an end user desires, they can cut into the loop where we apply this optimization scheme and impose whatever type of control sequence they would like. Mark, and then Dick.
That wasn't what I was
Okay.
I was going to ask you, could you put a little perspective on sort of granularity that you expect from manufacturing? So in other words, every 5 degrees in outdoor temperature, every 2 degrees in indoor wet weather, or something like that, to give an idea of how much work does the manufacturing have to go through to provide you with the data needed to calculate?
Yeah, great. In case anyone didn't hear, Mark was asking about the granularity of data that we're asking for from manufacturers. Basically, it depends on which independent variables the performance of your machine depends on. If you have 100% outside air hybrid, it's not going to be impacted by the room air conditions. The performance of that machine is completely independent, and so there's less data that we'll request. And all of that is kind of automatically built out in the spreadsheet that I showed. We ask for a full factorial combination of every independent variable with 3 levels. Does that make sense? So in each dimension, we ask for 3 different points and all of the different combinations of 3 different levels. Yeah. So it's a lot of information, but certainly I don't expect that these data tables would be developed from laboratory tests. It would take way too much time to run through each of these different points in a laboratory. But that's okay. Every manufacturer has some approach to modeling their own equipment, and what we're asking here is for them to package it together into a digestible form that others can actually do something reasonable with. Robbie, and then Curtis. Oh, yeah, that's right. Dick, you have a question?
Yeah, just, this approach is good. Energy Plus is primarily a polynomial curve fitting program. So are you developing a direct interpolation interface?
So Dick said that Energy Plus is primarily a polynomial curve fitting program. It's true most of the modules point at polynomial curves, though there is a module within Energy Plus that allows you to define lookup tables, and you can take any of those air conditioner models that are looking for curves, and you can literally just change the name to a lookup table, and it'll look up the lookup table instead. And the utilities that they have for these lookup tables can do a few different things. They can take the lookup table and create a polynomial curve set, if that's appropriate, or it can sort of ignore the fact that the air conditioner model is looking for a polynomial in particular and just give it the value that it needs. And so that utility already existed within Energy Plus, though it has limited dimensionality, and we worked with NREL through this project to extend the number of independent dimensions to 6. Which is what's appropriate.
Yeah, the reason I ask is a lot of our equipment now is getting complex. Like a typical rooftop now takes 3 models, not 1 model. So we take 3 equations, and we're finding that tables are a better approach because we can put head pressure control in them, we can put operational in them, so they become non-contiguous tables. So the way you're going is good.
Absolutely, and that's one of the reasons we ultimately chose to do lookup tables as well. The amount of data that's required to populate this model is not small by any means. However, I think it's really important for us to all admit that the things we're trying to do are complex, and there's not another way to represent the performance of this equipment with less data if you actually want to represent the performance of the equipment. So this is the detail about how this equipment performs. Robbie and Curtis?
I was wondering, how do you handle transients between
Currently, we're focused on steady state performance in each time step. And transients are definitely a limitation. I would suggest that the transients are going to be different for every type of hybrid system. And I don't think we have the knowledge yet to make a good prediction about how that will occur. So I'm not prepared to try to create a model that handles it. I'll also point out that most of the HVAC equipment modules in Energy Plus are also steady state performance. There are some ways that they integrate cycling performance for DX equipment, but not so much other types of steady state performance. I mean, transient performance. Curtis?
My question was regarding, you have a validation here, but you were also talking about a field validation, or are those real field test sites that you're validating with Energy Plus? And then, if so, are you going to get the baseline model to be validated prior to looking at your new model, or your new hybrid model?
So Curtis is asking about validation and how we're going about doing that, whether or not we're focused on validating our model against any field tests. We're not planning to do a validation against field tests during this summer. I hope that that's something that gets done in the relatively near future. However, we in particular decided not to try to validate against field performance because ultimately you're relying on multiple layers of model that are imposing error. You're first relying on developing an appropriate building model that matches the building that you're measuring from in the field, and then you're asking the question about the validation of our hybrid air conditioning model. So we are using field information for the performance of a real hybrid air conditioner. But what we've done is to take the capacity information of what that hybrid air conditioner did generate in the field and input that as the kind of desired conditions for our model to output and validate that our model is able to output the performance that the machine would have generated in those conditions. Basically, we've eliminated the uncertainty associated with the building model itself. In the back?
Have you quantified the benefit of the model? Like, how many hours you're saving, how many dollars you're saving? Like, I'd love to know what the commercial benefit is of commercial air conditioning.
We haven't studied it, but I think it's a trillion hours. And I'm sure that any energy modeler would agree. Any more questions? Thank you.